Okay, so most of the exercises for this chapter involve working with the delta function and verifying some properties of the delta function. In fact, most of them are things that we've already discussed. So I think the exercises for this chapter are relatively straightforward. There is one exercise, however, which is very important, and I wanted to discuss that with you a little bit. And that exercise consists of showing that let's do that. Good. It consists of showing that d3k over 2 pi cubed to omega k is a Lorentz invariant integration measure. So let's discuss this a little bit. So we want to show that this is equal to d3k primed over 2 pi cubed to omega k primed. Okay, now you can try to prove this for a general Lorentz transformation. I'm just going to give you a hint for a Lorentz transformation that corresponds to a boost along X. It would be great if you take this hint and turn it into a proof that this measure is invariant under any Lorentz transformation. And I think that you can do it. So try it. Try to do that exercise. Okay, so to explore how this measure would transform, let's spell out how the k prime and omega prime are related to the k and the omega. So k as a spatial vector has got three components. It's k1, k2, and k3. And when we write d3k, what we mean is we mean dk1 times dk2 times dk3. So what I want to do is I want to tell you how is omega k primed, k1 primed, k2 primed, and k3 primed, how are these related to omega k, k1, k2, and k3. And like I said, I'm going to do a boost along X. So by now, you can probably remember this. If someone woke you up in the morning at 2 o'clock in the morning, you wouldn't remember your own name, but you would remember how to write down a boost along the X direction, which is really great. So that's the Lorentz transformation for a boost along the X direction. There's a couple of trivial transformation laws in here. So one of them is that K2 primed is just K2. Well, that's pretty simple. And K3 primed is just K3. And then if we write down what is K1 primed, well, this one is non-trivial. So K1 primed would be equal to, just read it off the matrix. It's going to be a sinh phi omega k plus a cosh phi of K1. And to work out the Jacobian to go from between d3k and d3k primed, you're going to be taking derivatives of the k primes with respect to the k's. For k2 prime and k3 prime, this is pretty simple to do. But for the k1 prime, it is possible to make a mistake. So let me just point out one subtlety. So when you come to calculate, for example, dk1 primed dk2, what is this equal to? Now, you might initially think, oh, well, this is 0 because k1 prime depends only on k1, but watch out, this is not 0, okay? It's not equal to 0. And the reason why it's not equal to 0 is don't forget that omega k is equal to, so it's k dot k, so this will be k1 squared plus k2 squared plus k3 squared, so that's k dot k plus m squared square rooted. So omega k does depend on k2. It also depends on k3. So when you take this derivative, don't forget about the k dependence inside omega k. And then the other thing to bear in mind is that our transformation rule from the Lorentz transformation also tells us how omega k primed is related to omega k. So it's a cos phi omega k plus it is a sinh phi onto the k1. Okay, so you'll use that as well. So now you should really have enough of a hint to prove the invariance of this measure at the top of the page under a boost along the x direction. And if you're patient and you think a little bit, you'll be able to extend that to a proof of full Lorentz invariance for this measure. Okay, good. So good luck with the exercises. Keep practicing. That's how you get this subject. You practice as much as possible. And let's move on to chapter 4.